Bhishma Nirvana by Dr. Nilesh Oak. Chapter 5 Astronomy Agama. Consequently, he who wishes to attain to human perfection must therefore first study logic, next the various branches of mathematics in their proper order, then physics, and lastly metaphysics. Memonides. We will cover a few astronomy concepts that are relevant for chronology and sensitivity or error calculations of Bhishma Nirvana. 5.1 Celestial Time Clock. Let's begin with the analogy of mathematical clock and its mechanism with that of celestial clock. Various celestial motions are like the motions of various gears of the wheel train of a mechanical clock. While a power spring is the source of power that moves the wheel train in a mechanical clock, the gravitational forces and the interplay between them are responsible for the motions of the moon around the earth, motions of the earth, and the precession of equinoxes. We carefully control the settings of the wheel train and escapements mechanism in order to generate precise and accurate time on the display of a mechanical clock. In the case of archaeoastronomy, the task is to interpret astronomy observations in the context of the celestial clock in order to predict precise and accurate timing of either an ancient document containing those astronomy observations or ancient structure that was supposedly aligned according to astronomy coordinates of that time. The celestial clock appears complex, and it is, but so does a mechanical clock to a novice. On the other hand, a little patience and some willingness to comprehend the details is all that is required to understand both. Let's understand the celestial clock. The sun and the path of the sun as it appears to go around the earth, which we call ecliptic, is the reference point and the reference frame for our celestial clock. Thus, we will begin with the sun and the solar year. 5.1.1 Solar year. The solar year is the time interval required for the earth to make one complete revolution around the sun, measured from one vernal equinox to the next. This time interval is equal to 365 days, 5 hours, 48 minutes and 45.51 seconds. It is represented by a Gregorian calendar with 12 months and length of 365 days, unless it is a leap year when the length is 366 days. While the first day of the year in the Gregorian calendar is arbitrary in the sense that it does not coincide with any specific cardinal point, the Gregorian calendar has rules so that it closely approximates the solar year and will continue to do so for the next 8,000 years without introducing much inaccuracy. The focus of this popular solar calendar, that is Gregorian, to align the 4 days of cardinal points and keep them fixed by making appropriate corrections when required with the dates determined, for example, 21st June and 21st December, 23rd March and 23rd September, 4 cardinal points. Solar months are 12 in number in Gregorian calendar system, and the length of each month is arbitrarily set so that all days of the year together add up to 365 days. 5.1.2 Solar day. It is defined as the length of time that elapses for the sun to reach its highest point in the sky 2 consecutive times. The duration is approximately 24 hours. This is our most familiar 24-hour day. Inventions of mechanical and now digital clocks allow us to measure it from any arbitrary reference point such as midnight as it is done in our times. 5.1.3 Solar month. True solar month would or should refer to the time interval when the sun stays in the region of a specific zodiac. However, this method is not followed by any existing solar calendars. In that sense, duration and names of solar months like January through December of Gregorian calendar are arbitrary. 5.2 Lunar cycles. 5.2.1 Lunar year. The moon takes 27.3 days to make a complete round trip around the earth. However, the earth itself moves by a significant distance during this time and thus it takes the moon around 29.5 days to reach the same phase with respect to the earth. This is lunar month. The length of time for the moon to make one revolution in its orbit is difficult to predict and varies from its average value. Because observations are subject to uncertainty and weather conditions, and astronomical methods are highly complex, there have been attempts to create fixed arithmetical rules. The average length of synodic month is 29.530589 days. The lunar year is made up of 12 such lunar months, and thus the length of the lunar year is equal to 29.5 multiplied by 12, which is 354 days. The Islamic calendar follows the lunar year. Since the lunar year is shorter by 10 to 11 days from the solar year, Islamic holidays occur 10 to 11 days earlier each subsequent year. For example, the month of Ramadan occurs earlier by a month with respect to the solar calendar every 3 years. This also means if the month of Ramadan occurs during the peak of winter in any given year with respect to Gregorian calendar, it will occur at the peak of summer in 18 years in the future. 5.2.2 Tithi or lunar day. In the Indian calendar system, which is luni-solar year system, a Tithi is a lunar day or the time it takes for the longitudinal angle between the moon and the sun to increase by 12 degrees. Tithi begins at varying times of the day and vary in duration from 19 to 26 hours. There are 30 Tithis in each lunar month. Amavasya is new moon or no moon day, and it is followed by Pratipada 1, Dvitiya 2, Tritiya 3, Chaturthi 4, Panchami 5, Shashti 6, Saptami 7, Ashtami 8, Navami 9, Dashmi 10, Ekadashi 11, Dwadashi 12, Trayodashi 13, Chaturdashi 14, and Purnima, that is full moon day. These Tithis are then repeated for the second half of the lunar month, beginning with Pratipada, Dvitiya, etc., and end with Amavasya when a new lunar month begins. The Mahabharata method of referring to the day is by referring to the nakshatra closest to the moon. One can determine the lunar month with reasonable accuracy by knowing the nakshatra of the day along with the paksha and the phase of the moon. The lunar day or tithi and the nakshatra of the day is not same as the day defined by the rising and setting of the sun. The lunar day, tithi, and or the nakshatra of the day could be determined by simply noting down the phase of the moon and or the nakshatra close to the position of the moon. The lunar day, tithi, can also be calculated mathematically. The timing of an observation and an error on the part of the observer may lead to an error of plus or minus 1 day, that is 1 lunar day or nakshatra, in noting down the phase or position of the moon. In the Indian calendar system, aha may refer to a time interval when the sun is above the horizon, and ratra may refer to the time interval when sun is below the horizon, and ahoratra as referring to the modern 24 hours day. It is important to note that the word aham or ratra were also used to designate a 24-hour day in Mahabharata times. A day was further divided into muhurtas. 30 muhurtas is equal to 1 day is equal to 24 hours, which were in turn further divided into smaller units. 5.2.3 Nakshatra or wives of the moon. The predictable rising of the sun provided the ancients a unit of time. However, to track the progress of time, one aspires to monitor the motion of a moving object with respect to a non-moving object. Non-moving only in a relative sense, since all astral bodies are in motion. Observations of the moon's position, which is a moving object, with respect to those of the nakshatras, which are relatively not moving, at night provided such an opportunity. Astronomers of the Mahabharata era used the system of nakshatra ganana developed by their predecessors to keep track of time. A nakshatra, which is loosely translated as asterism, could be either a specific star, for example Chitra, or a group of stars, for example Kritika. along the ecliptic and is employed as a reference in noting down the positions of astral bodies like sun, moon, planets, comets, etc. Additional evidence is emerging from the pages of ancient Indian narratives that allude to varying numbers of nakshatras employed by ancient Indian astronomers. However, the logic and rationale behind such varied systems is not clear at this time. What is clear is that the epics have made use of nakshatra systems with 27 or sometimes 28 nakshatras. The average angular space of nakshatra was mathematically defined based on the 360 degrees divided by the number of nakshatras assumed in the system. It appears that the desired numbers of nakshatras were determined based on how long it took the moon to complete one orbital cycle. Since the moon completes one cycle through its orbit in 27.3 days, 27 nakshatras were selected. This nakshatra system was also used to track positions of other astral bodies. Since the moon visited each nakshatra once every month, poetically it was perceived as moon visiting each of his 27 wives each day of the month until the moon visited all of them only to repeat the cycle during the next month. These wives of the moon were given specific names, were assigned a devata or deity, and are frequently referred to by the name of their assigned deity. The nakshatras, along with their yogatara and nakshatra deity, are listed in Table 1. Some nakshatras have synonyms and were recognized by those synonyms in addition to being referred to by their presiding deity. For example, Bhadrapada is also called Proshtapada. Dhanishta is also called Shravishta, and Shatabhisaj is called Shatataraka. Some variations can also be seen while assigning a presiding deity to a given nakshatra. These variations, fortunately, do not lead to any confusion. Existence of other evidence and cross-references within Indian literature are sufficient to understand the nakshatra being referred to. The nakshatra closest to the moon on a given day is the nakshatra of the day in the Indian calendar system. Determination of the nakshatra of any given day based on visual observations can lead to an error of plus or minus 1 day. 5.2.4 Lunar Month. There are two definitions of lunar months, Purnamanta and Amanta. A lunar month that begins with the full moon day and ends on the next full moon day is called Purnamanta. A lunar month that begins on Amavasya or new moon day and ends on the next Amavasya is called Amanta. We will follow the definition of Amanta lunar month throughout the book. In the Amanta system, lunar months are named after the nakshatra near full moon during that month. Lunar months are named as Chaitra, Vaishakha, Jeshta, Ashada, Shravana, Bhadrapada, Ashwin, Kartika, Margashirsha, Pausha, Magha, and Falgun. 5.3 Luni-solar year. The Gregorian calendar and the Islamic calendars are examples of purely solar and purely lunar calendars, respectively. The Indian calendar is decidedly luni-solar from ancient times. The Indian calendar does have regional variations. However, the core of it can be described without getting into regional nuances. The basic unit of the Indian calendar is the lunar day, which we call Tithi. For the purposes of defining a year, the next unit of the Indian lunisolar calendar is the lunar month. The lunar month is a time interval either from one new moon to the next or from one full moon to the next. The Indian lunisolar calendar is Nirayana in nature. The Nirayana year is the time taken for the sun to return to the same fixed point on the ecliptic. The Nirayana year comprises 12 solar months. The lunar year consisting of 12 lunar months, and that is shorter than the solar Nirayana year, and hence Adhik Masa or leap months must be added periodically so that the calendar approximates the Nirayana solar year. The occurrence of Adhik Masa is not or cannot be determined by arithmetical rules of the Gregorian calendar. Additionally, some lunar months in the Amanta Luni solar calendar can have skipped days or tithis or repeated days or tithi, which makes the numbering of the days in the month slightly more complicated than usual. Length of a lunar month is approximately 29.5 days, and therefore length of the lunar year is 12 multiplied by 29.5, which is 354 days. Length of the solar year is 365.2422, around 365 days, and difference between solar and lunar year is 365 minus 354, approximately 11 days. 5.3.1 Adhik Masa. Indian calendar makers came up with the ingenious idea of Adhik Masa, or extra lunar month, to enable synchronization between the solar and the lunar year. While the method or methods to determine Adhik Masa might have changed over the millenniums, the invention of Adhik Masa is very old. Not only the Rig Veda, but also the Mahabharata refers to Adhik Masa, and thus we have reasons to believe that the existence of Adhik Masa during the Ramayana times, since the Ramayana is post Rig Veda but before the Mahabharata, I did not require the assumption of Adhik Masa in my Ramayana research. Rather, the point I want to emphasize is that the existence of Adhik Masa in calendar calculations during Ramayana times should not surprise us. While references to Adhik Masa exist in the Rig Veda and the Mahabharata, no specific method to determine Adhik Masa is mentioned. However, to clarify the concept of selection and naming of Adhik Masa, I will illustrate the method employed in India in our times. Recall that the lunar month begins with Amavasya in Amanta reckoning, and that the moon and the sun are together as seen from the earth on Amavasya day. The ecliptic path of the sun is divided into 12 zodiacs or 27 nakshatras, and thus each zodiac is approximately 30 degrees 1/12 of the ecliptic. This also means that on an average, the sun will travel through the area of each zodiac in approximately 30 days. The sun transiting from one zodiac into the next is called Sankranti. Sankranti means meaningful movement or transition. Typically, Amavasya or new moon day falls only once between two Sankrantis. However, occasionally Amavasya may fall twice while the sun is still transiting through the area of single zodiac. The lunar month defined by this second Amavasya day is named as Adhik Masa. Let us analyze the basis of Adhik Masa calculations. The earth is revolving around the sun. The earth completes one circle around the sun in 365.2564 days. That is 365 days, 6 hours, 9 minutes and 12.96 seconds. Whereas the moon takes 29.5306 days or 29 days, 12 hours, 44 minutes and 3.84 seconds from the new moon or Amavasya to the next new moon, that is next Amavasya. Therefore, the duration of lunar month is 29.5306 days, and the number of days in 12 lunar months is 29.5306 into 12 is 354.3672 days. The difference between a solar year and the lunar year is 10.8992 days, which is approximately 11 days. Therefore, every year, lunar months and thus the tithis occur 11 days earlier. In 3 years, this difference reaches up to 33 days, which is more than 1 month. This difference necessitates insertion of an Adhik Masa every 3 years. The timing of Adhik Masa varies. It may come after an interval of 2 years and 4 months, 2 years and 9 months, 2 years and 10 months, or 2 years and 11 months. On average, an Adhik Masa comes in 2 years and 8.5 months. This value can be verified by dividing the duration of lunar month, that is 29.5 days, by 10.9. A lunar year is 10.9 days shorter than a solar year, and therefore, after dividing 29.53 by 10.9, which is approximately 2 years and 8.5 months, there arises a difference of 1 month. 5.3.2 Kshaya Masa. Recalling that usually Amavasya, that is new moon, falls once between two Sankrantis, Sankrantis being the sun's transit into the area of the next zodiac. On a rare occasion, no Amavasya would occur between two Sankrantis, and when that happens, the subsequent lunar month is considered as Kshaya or elapsed Masa. Let us understand why this may happen. The minimum value between the two Sankrantis is 29 days, 10 hours and 48 minutes. And the maximum value is 31 days, 10 hours and 48 minutes. Whereas the minimum value between two Amavasyas, that is two new moons, is 29 days, 5 hours, 54 minutes and 14 seconds. And the maximum value between two new moons is 29 days, 19 hours, 36 minutes and 29 seconds. Therefore, it so happens, although rarely, that no Amavasya or new moon falls between two Sankrantis. This generally happens after 19 years or after 141 years and sometimes after 65 or 76 or 122 years. This type of situation is termed as Kshaya Masa. This is possible during the sun's transit through zodiacs with smaller areas such as Scorpio, Sagittarius and Capricorn. This implies that Kshaya Masa most likely happens during the lunar months of Margashirsha, Pausha or Magha. 5.3.3 Why synchronize lunar and solar calendars? While the Tithi or lunar day is a unit for daily measurements of time and the lunar month is a unit for monthly measurement of time, it is the solar year that determines the seasons. In agrarian cultures, the importance of synchronizing lunar and solar years is obvious. This is also true for a culture that is deep in commerce and distant navigation. Synchronizing lunar days and months with solar year is critical for planting and harvesting of crops and ensuring safe navigation. Celebration of festivals, initiation and completion of yajnas, and strict adherence to rituals on specific days of the year were all meant to informally educate the society and to aid in maintenance of the calendar. 5.4 Seasons or Ritus. 6 seasons were recognized with each season made up of approximately 2 lunar months. The seasons or Ritu were designated as Vasanta, spring, Grishma as summer, Varsha as rain, Sharad is early autumn, Hemanta late autumn and Shishira winter. The seasons of Vasant is centered around the day of the spring, which is vernal equinox. 2 months leading to the day of the summer solstice constituted the season of Grishma, while 2 months following the day of summer solstice constituted the season of Varsha. The season of Sharad centered around the day of the fall, that is Sharad equinox. 2 months leading to the day of winter solstice constituted the season of Hemanta, while 2 months following the day of winter solstice constituted the day of Shishira. 5.5 Precession of the Earth's axis or precession of equinoxes. The precession of equinoxes is the phenomenon of movement of the Earth axis in a circular path that takes about 26,000 years to complete one cycle. As the Earth axis moves through the circular path, it traces a circle in the sky at any given time where the Earth's axis points to, along with its circular path, is called the point of North Celestial Pole or NCP. If a distinct and visible star is close to this point of NCP, it attains the status of a North Pole star for a time, that is until the NCP moves far away from the position of the star. The modern European world became aware of this phenomenon of the precession of the Earth's axis only very recently, about 2000 years ago, via observations of Egyptians, since the observations that led to this awareness were based on the movement of the point of the equinoxes, the phenomenon was mislabeled as the precession of equinoxes. Unfortunately, the name has stuck and it is now widely used in modern astronomy literature. This phenomenon of precession of Earth's axis, which is called ayana, and its corresponding consequences, coupled with ingenious Indian invention of lunisolar calendar, is responsible for our ability to analyze astronomy and chronology references from ancient Indian narratives and to determine the chronology of ancient Indian civilization and by implication ancient civilizations of the world. 5.5.1 Change in the location of the North Celestial Pole NCP. The precession of the Earth's axis results in change of location of the North Celestial Point NCP. Thus, a bright star that can act as visible proxy for the NCP would also change with the change in the location of NCP. For example, while Polaris is the North Pole star in our times, Vega or Abhijit or Brahmarshi was the North Pole star around 12,000 BCE. 5.5.2 Change in the position of the Sun. The timing, which is day, lunar month and tithi of the winter solstice would shift with respect to the background reference frame of a nakshatra by about 1 day or 1 degree every 72 years. This means the point of winter solstice would shift by about 1 nakshatra every 1000 years. The calculation is 26,000 divided by 27, which is approximately 963 days, approximating 1000 days. In our times, 21st century or 2100 CE, the position of the Sun is between Nakshatra Mula and Nakshatra Purva Ashada on the day of the winter solstice, and it is between Nakshatra Ardra and Nakshatra Mrigashirsha on the day of the winter solstice, given in figure 4. If we go back in antiquity by about 7,500 years, the position of the Sun for the day of the winter solstice would shift from Nakshatra Mula and Purva Ashadha to Nakshatra Uttara Bhadrapada, and the position of the Sun for the day of the summer solstice would shift from Nakshatra Ardra Mrigashirsha to Nakshatra Hasta and Purva Falguni. A shift of about 7 nakshatras would occur as expected, corresponding to 7,000 years. 5.5.3 Shift of seasons with respect to lunar months. The lunar month of Chaitra occurs during the second half of Vasanta Rutu or spring in our times. If we go back halfway through the cycle of the precession of equinoxes to 11,000 BCE, the lunar month of Chaitra coincided with the second half of Sharad Rutu or pre-autumn. The lunar month of Ashwin occurs during the second half of Sharad Rutu, pre-autumn in our times. If we go back halfway through the cycle of the precession of equinoxes to about 11,000 BCE, the lunar month of Ashwin coincided with the second half of Vasant Rutu, which is spring. In other words, all cardinal points, solstices and equinoxes had reversed from 2016 CE versus 11,000 BCE. 5.6 Julian and Gregorian calendars. The Julian calendar, a reform of the Roman calendar, was introduced by Julius Caesar in 46 BCE and came into force in 45 BCE. It was designed to approximate the tropical year. It has a regular year of 365 days divided into 12 months and a leap year added to February every 4 years, which makes the average Julian year 365.25 days long. The Julian calendar overestimates the length of the year by 0.0078 days. And this discrepancy results in the shifting of equinox or solstice days over a long period. The Gregorian calendar was introduced in 1582 CE. The Gregorian calendar modified the Julian calendar's regular cycle of leap years, which is years exactly divided by 4, by introducing a caveat: every year that is exactly divisible by 4 is a leap year except for years that are exactly divisible by 100, and the centurial years that are exactly divisible by 400 are still leap years. Thus, the year 1900 is not a leap year, but the year 2000 is a leap year. This modification changed the mean length of the calendar year from 365.25 days to 365.2425 days. The Gregorian calendar also dealt with the past accumulated difference between these lengths. The Roman Catholic Church thought that the First Council of Nicaea had fixed the vernal equinox on 21st March, and by the time of the Gregory Edict for the modification of the calendar in 1582 CE, the vernal equinox had moved backward in the calendar and was occurring on about 11th March, 10 days earlier. The Gregory calendar therefore began by dropping 10 calendar days, 5th to 14th October in 1582 CE, to revert to the previous date of the vernal equinox. The marginal difference of 0.000125 days between the Gregorian calendar average year and the actual year means that in around 8,000 years, the calendar will be about 1 day behind where it is now. It is important to remember that the Earth's rotation also experiences some variation, and thus the change in the length of the vernal equinox year cannot be accurately predicted. Historical research uses the Gregorian calendar for the events after the 16th century and uses the Julian calendar for the events before the 16th century. 5.7 Delta T and the dynamic time. This is the difference between universal time UTC and the terrestrial dynamic time TDT. TDT is based on atomic clocks and it is the standard for the precise timekeeping in astronomy. It differs from UTC because the Earth's rotation is showing in an irregular manner. This is due to the Earth's gravitational interaction with the Moon. We must periodically add or subtract leap seconds to and from UTC to keep it in sync with where the Earth is pointing. The accumulated difference between UTC and TDT is called delta T. The current value of delta T is about 67 seconds. But in 4000 BCE, the accumulated time correction was about 2 days. And in much earlier periods, it was only an educated guess. Note that delta T affects the time when an astronomical event is observed on Earth and hence the altitude and azimuth where it is seen in the sky. 5.8 Caution while using the solar calendar as reference. The Julian calendar experiences the shift of 1 day every around 128 years in the timing of the day of the winter solstice. For example, it was assumed that the day of the winter solstice occurred per this Julian calendar on 21st December during the year 45 BCE. This meant after 128 years, around 83 CE, the day of the winter solstice began occurring on 20th of December. As one goes further in antiquity, beyond 45 BCE, the day of winter solstice would shift by 1 day on Julian calendar every 128 years, but in the opposite direction. For example, the day of the winter solstice occurred on 31st January in the year 5560 BCE. The current solar calendar in use is Gregorian calendar. The usage of this calendar began in 1582 CE. Per this calendar, the day of the winter solstice is fixed at 21st December. The scenario will continue without significant change for a foreseeable future. 5.9 What is Central Tithi? Trademark. I introduce a new concept called Central Tithi, trademark. I have employed this concept at least since 2009 CE. However, I had used other names such as Median Tithi. Central Tithi is the most appropriate name. Median Tithi is not correct and will mislead many, especially those familiar with the definition of median from statistics. To understand the concept of Central Tithi, it is useful to ask the following question. If the day of the winter solstice is fixed at 21st December per current solar reference calendar, which is Gregorian, what is the lunar Tithi and lunar month for this day of the winter solstice? We would not be able to easily answer this question. We will require additional information, for example, which specific year. If you take say 1999 CE, and even then we will need to perform additional calculations or refer to a panchang for that specific year to answer the question of lunar tithi and lunar month. In 1999 CE, the tithi for the day of the winter solstice was Margashirsha Shukla, that is 14 Chaturdashi. This is because lunar tithi and the lunar month for the day of the winter solstice is not fixed, unlike 21st December of Gregorian calendar. Recall that there is a gap of about 10 to 11 days between the lunar year and the solar year, with the lunar year shorter by 10 to 11 days, and this means a lunar tithi would shift by about 10 to 11 tithis every year for the day of the winter solstice, while the solar day per solar reference calendar would remain fixed at 21st December. Of course, this shift will not continue forever. After about 2-3 years, the lunar year would be synchronized with the solar year by the insertion of Adhik Masa, which would result in an abrupt change of the tithi for the day of the winter solstice. After this abrupt change, the tithi would shift by about 10 to 11 days until it is time for another Adhik Masa. If we plot lunar tithis for the day of the winter solstice for the last 20 years, 1998 to 2017 CE, they would occur over an interval of Margashirsha Shukla 10 through Pausha Shukla 9. The broad interval of about a month-long duration, that is 30 tithis, over which the day of the winter solstice would coincide, is centered around the tithi of Margashirsha Vadya or Krishna Navami 9. Thus, in our times, the central tithi for the day of the winter solstice is Margashirsha Vadya or Krishna Navami 9. Thus, a central tithi is the tithi around which the actual tithis for the specific day of cardinal points would occur, plus or minus 15 tithis. 5.10 Central tithi and the precession. Since the point of the winter solstice would move by 1 degree with respect to the background nakshatra reference frame due to the precession of Earth's axis every 72 years, the central tithi would also shift by 1 tithi every 72 years. 5.11 Day of the winter solstice. The day of the winter solstice occurs on 21st December per Gregorian reference calendar in our times. That has been the situation since the Gregorian calendar came into being in 1582 CE. This will continue to be the case for next 3000 years. The Gregorian calendar uses a particular rule for leap year. Every year that is exactly divisible by 4 is a leap year, except for the years that are exactly divisible by 100, but these centurial years are leap years if they are exactly divisible by 400. For example, the years 1700, 1800 and 1900 are not leap years, but the year 2000 is. The Julian calendar is believed to have begun in 45 BCE. The day of the winter solstice was set at 21st December. Since Julian calendar assumes leap year every 4 years, it ends up shifting the day of the winter solstice by 1 day every 128 years. This is the reason for a correction of about 10 days had accumulated by the time of the institution of Gregorian calendar. It is a convention to use Julian calendar as reference calendar for all events prior to 1582 CE. For our purpose, it is important to remember that the day of the winter solstice would shift by 1 day every 120 years as we go back in antiquity, beginning with 45 BCE, the reference year of the Julian calendar, when the day of the winter solstice was set to 21st December. Thus, the day of the winter solstice was on 5th January in 1951 BCE, on 7th January in 2155 BCE, on 8th January in 2448 BCE, on 13th January in 3066 BCE, on 14th January in 3142 BCE, or 3162 BCE and on 30th January in 5560 BCE. Chapter 6 Constraints on the Events of Bhishma Nirvana. Problems are hidden opportunities, and constraints can actually boost the creativity. Martin Villeneuve. We documented all relevant chronology evidence of Bhishma Nirvana, and the results of that investigation can be summarized as follows. 1. Bhishma was on the bed of arrows for more than 92 days. We will use 92 as the lower limit in estimating the constraints related to the events of Bhishma Nirvana. It is important to keep in mind that actual duration is more than 92 days. 2. Bhishma fell in the battle on the 10th day of the war, and since then he was on the bed of arrows until the day of the winter solstice. The war continued for additional 8 days. 3. Yudhishthira and his party spent a month-long interval on the bank of the Ganga river after the war was over and before returning to Hastinapura. 4. In Hastinapura, Yudhishthira was coronated as the king and then he went to meet Bhishma. It is on this day that Krishna told Bhishma that Bhishma had 56 more days to live. 5. Yudhishthira visited Bhishma every day for 6 consecutive days, during which Bhishma advised him on various subjects of Rajadharma and Mokshadharma. Bhishma recited Vishnu Sahasranama on the 6th and the last day, and then asked Yudhishthira to return to Hastinapura and only return to him when the sun turned north, that is, after the day of the winter solstice. 6. Yudhishthira returned to Hastinapura and stayed there for 50 nights before returning to Bhishma. Bhishma passed away on that day. We documented all relevant astronomy evidence of Bhishma Nirvana, and the results of the investigation can be summarized as follows. 1. Most of the 18 days of Mahabharata war took place during the first part or first month of the Sharad season. 2. The Mahabharata war began on the Amavasya day plus or minus 1 day and ended 3 to 4 days after the Purnima day, that is, the war began and took place during the Shukla Paksha or waxing phase of the lunar month. 3. The Mahabharata war began on the day of Amavasya and took place during the lunar month of Margashirsha. 4. The inference of war beginning with Amavasya and thus taking place during the Shukla Paksha of the lunar month of Margashirsha is further validated by references to the occurrence of Kartik Purnima and Kartik Krishna Chaturdashi before the beginning of the Mahabharata war. 5. The inference in 4 is further corroborated by the occurrence of Chaitra Purnima long after the day of Bhishma Nirvana. We also introduced the new concept of central tithi in the chapter on Astronomy Agama. We will combine the chronology and astronomy evidence against the background of astronomy science to establish these constraints using the scientific framework of Pratyaksha Anumanagamaha Samadhipat 7 of sage Patanjali and Pratyaksha Anumanopamana Shabda Gautam Krut Nyaya Darshan 113 of Gautama. In both cases, the importance of drawing the inference based on objectively testable evidence is emphasized. This can be represented as follows. The framework is important for our analysis and we will make ample use of it to illustrate how we arrived at our inferences. 6.1 Constraints on the timing of the Mahabharata war. We will explore the constraints on the season, lunar paksha, that is fortnight, and lunar month of the Mahabharata war. 6.1.1 The season of the Mahabharata war. Bhishma Nirvana occurred on the day or 1 day after of the winter solstice, and since Bhishma was on the bed of arrows for 92 plus days, we can infer that the Mahabharata war itself took place during the first half of Sharad season. We can explain this inference using the triad of explanation, prediction, testing as follows. 6.1.2 The lunar paksha of the Mahabharata war. The Mahabharata text does not refer to the description of the moon during the first 7 days of the war. The descriptions of the full moon-like moon appear beginning with the 10th day of the war and continue for 2 days after the war. The last few days of the war, including 2 days following the war, are rich in full moon descriptions. We can infer via Pratyakshanumano Pamana Shabda that the war began near Amavasya day and most of it took place during the Shukla Paksha or waxing phase of the lunar month. 6.1.3 The lunar month of the Mahabharata war. The Mahabharata text preserves a few critical references that point to phases and positions of the moon that allow us to identify Margashirsha as the lunar month of the Mahabharata war. 6.2 The lower limit of the Tithis of Mahabharata events. The lower limits of the Tithis define the earliest occurrence of the events within the lunar year of the Mahabharata war. We will employ available evidence to determine the lower limits on lunar Tithis for the following events. 1. First day of the Mahabharata war. Number 2. The 10th day of the Mahabharata war when Bhishma fell in the battle. Number 3. The day of Bhishma Nirvana that occurred either on the day of winter solstice or a day after. 6.2.1 The first day of the Mahabharata war. The Mahabharata text states that occurrence of Kartik full moon and Kartik Krishna Chaturdashi before the war began. Thus, the lower limit of lunar Tithi of the first day of Mahabharata war is that of Kartik Amavasya or Kartik Krishna 15. This means that the first day of the Mahabharata war cannot be any Tithi before the Tithi of Kartik Amavasya. 6.2.2 The 10th day of the Mahabharata war. Fall of Bhishma. Once the lower limit on the first day of the Mahabharata war is set, the lower limit on the 10th day of the war is set automatically. We can count 10 Tithis from the lower limit of the first day of the war and arrive at Margashirsha Shukla Navami or 9 as the lower limit of the 10th day of the war when Bhishma fell in the battle and decided to rest on the bed of arrows until the day of Bhishma Nirvana. This means that the 10th day of the Mahabharata war cannot be any Tithi before the Tithi of Margashirsha Shukla Navami 9. 6.2.3 The day of Bhishma Nirvana. Since we know that Bhishma was on the bed of arrows for more than 92 days, we will employ 92 as the lower limit on his duration on the bed of arrows and then begin counting from the lower limit of the 10th day of the war, Margashirsha Shukla Navami, to arrive at Falgun Shukla Dwadashi 12 as the lower limit for the day of Bhishma Nirvana. This means that the day of Bhishma Nirvana cannot be any Tithi before the Tithi of Falgun Shukla Dwadashi 12. 6.3 The upper limits. The upper limits of the Tithis define the latest occurrence of the events within the lunar year of the Mahabharata war. Since we are going to estimate the upper limits for the identical 3 events, first and 10th day of the war plus the day of Bhishma Nirvana, we will explore them in the reverse order. 6.3.1 The day of Bhishma Nirvana. The Mahabharata text tells us that Bhishma Nirvana occurred long before the day of Chaitra Purnima, that is full moon. However, it does not provide any additional chronological clues. This significant gap between the day of Bhishma Nirvana and Chaitra Purnima can be asserted because sufficient time, whatever that may be, elapsed between the two events, enough for Krishna to visit Dwarka after the day of Bhishma Nirvana and to return to Hastinapura before Uttara gave birth to Parikshit. The Pandavas were not at Hastinapura when Parikshit was born. The Pandavas returned to Hastinapura with much wealth, and this is when Vyasa suggested initiation of Ashwamedha Yajna on the upcoming day of Chaitra Purnima. Instead of guessing a number of days between the day of Bhishma Nirvana and Chaitra Purnima, we will employ Chaitra Purnima as our upper limit on the Tithi of Bhishma Nirvana. Still, it would be useful to keep in mind that Bhishma Nirvana indeed occurred long before the day of Chaitra Purnima. This means that the day of Bhishma Nirvana cannot be any Tithi after the Tithi of Chaitra Purnima or Chaitra Shukla 15. 6.3.2 The 10th day of the war. Things become very interesting and intriguing as we estimate the upper limit for Tithi of the 10th day of the war. Beginning with the day of Chaitra Purnima and counting backward by 92 days lead us to the Tithi of Pausha Shukla Dwadashi 12. It means that the 10th day of the Mahabharata war cannot be any Tithi after the Tithi of Pausha Shukla Dwadashi. On the other hand, we have two specific constraints for the 10th day of the war. 1. The day must occur during the lunar month of Margashirsha. 2. The day must occur during the Shukla Paksha of the lunar month. These two constraints demand that the 10th day is further moved back by first 12 days, that is 12 days related to lunar month of Pausha, and then by additional 15 days for the Krishna Paksha of Margashirsha. This movement, due to such constraints, brings the 10th day of the war within the grasp of Shukla Paksha of Margashirsha. On the other hand, enormous evidence based on the phases and positions of the moon of the Mahabharata text asserts that this is not going to be enough to satisfy other constraints. For example, 1. The first day of the war cannot be removed from the day of Amavasya more than one day. 2. The lunar month of the war must be that of Margashirsha. And 3. The constraints of having most of the days of the war during the Shukla Paksha of Margashirsha. A surprising, intriguing and impressive conclusion is staring in our face. What is it? The conclusion is that there is no range over which we can determine the tithi for the 10th day of the war. Thus, the upper limit on the 10th day of the war is same as its lower limit. The maximum we will be able to coax out of these constraints is the ordinary and allowed error of about plus minus 1 day due to the variable lengths of tithis. The conclusion is that the 10th day of the war when Bhishma fell on the battle is fixed as Margashirsha Shukla Navami 9. This means the 10th day of the Mahabharata war cannot be any other tithi but the day of Margashirsha Shukla Navami. 6.3.3 The first day of the war. The upper limit for the first day of the war is a bygone conclusion. All the restrictions and a little error allowed for the 10th day of the war also applies to the first day of the war. So the conclusion is that the first day of the war is fixed at Kartika Amavasya. This means that the first day of Mahabharata war cannot be any other tithi but the day of Kartika Amavasya, Kartik Krishna 15. Summary. The first day of the Mahabharata war was the day of Kartik Amavasya, Kartik Krishna 15. The 10th day of the Mahabharata war was the day of Margashirsha Shukla Navami 9. The lower limit for the tithi of Bhishma Nirvana is Falgun Shukla 12 and the upper limit for the tithi of Bhishma Nirvana is Chaitra Purnima. This means Bhishma Nirvana occurred after Falgun Shukla Dwadashi 12 and before Chaitra Purnima Chaitra Shukla 15. The story continues in chapter 7.